Right, so now we start the proper mathematics. This is the same section 1 as was given in 2007, which means that you've got access to at least some written notes and some audio from 2007, I think, if you check the web page. Certainly for, if not for the very first lectures, where there may have been technical problems, certainly for later. So we'll start by revising complete metric spaces a bit and moving on to some stuff that you probably haven't seen before. So this is about complete metric spaces, but also about complete metrizable spaces, which is something different. That's about topological spaces. And there's a subtle difference, as we'll see, between the notions of being a complete metric space and being a complete metrizable topological space. So what is complete metric space? Well, it means that every Cauchy sequence in the space converges. If any of these terms seem unfamiliar, then that will be part of the revision you need to do from metric and topological spaces, and we are discussing that on Friday. So you should have a look at the 2 exam papers I gave out copies of from metric and topological spaces. If you haven't got those, then you should try and get copies from me, and we'll discuss any queries you've got about that on Friday. If we get through the queries quickly, then we'll just carry on with this section. So every Cauchy sequence should converge. Otherwise, it's an incomplete metric space, which means at least one Cauchy sequence which doesn't converge. And then you can talk about the metric being a complete metric or an incomplete metric. But the problem is that completeness is not a topological property. So what do I mean by that? It means that, well, a topological property of a topological space is one which is preserved by homeomorphism. But the problem is that you can have complete metric spaces that are homeomorphic, as topological spaces, to incomplete metric spaces. Did I say that the right way around? Anyway, you can have one that's complete and the other one that's incomplete, and they could be homeomorphic. So what's an example? Well, example, R and the unit interval 0, 1 are homeomorphic when you use the usual metrics. But R is complete and the open interval 0, 1 isn't. So what does that mean? It means that from the point of view of the topology, you can't tell the difference between the real line and the open interval 0, 1. Topologically speaking, they've got the same structure of open sets. Any topological properties you have of one will be true of the other, and so on. But obviously, when you use their usual metrics, you get a lot of things different about them. For example, the open interval 0, 1 is bounded as a metric space, whereas the real line is not bounded as a metric space. So the extra information you're getting from the metric is actually making these spaces different from each other. But if you don't care about the extra detail you get from the metric, and you're only interested in the open set structure, and in fact about continuous functions and things like that, so if you're only interested in things about something to do with continuous functions, you're not going to care, you're only going to care about the open sets, you're not going to care about the metric precisely, as long as you get the same open sets, then you can't tell them apart. So you have to come up with some sensible notion that incorporates the information, which is a topological property, but which tells you something about whether there's some sort of complete metricness involved. And this is the notion of complete metrizability. So what does it mean to say that a topological space is complete metrizable? That means that you can find some complete metric on it which does induce the topology. So you start with just a topological space and you haven't got any metric at all. Now the first thing that could happen is you've got a topological space. There may be no metric at all that induces the topology. when there is a metric that induces the topology, there may be several different ones. There'll usually be lots of different ones. And it could be that some of the metrics that give you the topology are incomplete, and other metrics that give you that topology are complete. Or it could be that all of the metrics that give you the topology are incomplete. And under some circumstances, all of the metrics that give you the topology have to be complete. So there are various things that can happen. You can think about all the different possible cases. We've got one example here. You can change the metric on the open interval 0, 1 in order to make it into a complete metric space. How would you do that? You could transfer across. You can take your homeomorphism, whatever your favorite homeomorphism is, from the real line to the open interval, or from the open interval to the real line, and you could use that homeomorphism to transfer the metric across from the real line to the open interval. You can do that whenever you've got a bijection. You can transfer metrics between two spaces. If you've got a bijection between two spaces and you've got a metric on one of them, you can pull it over using the bijection and give you a metric on the other one. And under those conditions, you end up with an isometric metric space to the original. And isometries, isometric metric spaces, do share properties like completeness. So if you pull over the usual metric from the real line and use it to give you a metric on the open interval, you get a complete metric on the open interval. But because you're using a homeomorphism to pull it over, that metric you pull over is a complete metric on the open interval. So it's a little bit subtle, but it means that the usual metric, although the usual metric on the open interval is incomplete, there is an equivalent metric, one which gives the same topology, which makes it complete. And if you think about it, using what I said about transferring metrics across, and if you've got any queries about that, let me know. I can give you more details. It's a sort of standard construction, pulling metrics around using bijections, or various things like that. Then, so being complete metrizable is in fact equivalent to saying that X is homeomorphic to some complete metric space. And that is obviously a topological property, because if two topological spaces are homeomorphic and one of them is homeomorphic to a complete metric space, then the other one's going to be homeomorphic to the same complete metric space. So the fact that this is a topological property is then immediately obvious. And for most purposes, if you've got a theorem about complete metric spaces, then it's almost always true for complete metrizable topological spaces, because you just bring in your complete metric, which induces the same topology, and you use your theory about complete metric spaces. So in fact, if you've got topological results about complete metric spaces, they should usually be expressed in terms of complete metrizable spaces instead. Any questions so far about the difference between complete metric spaces and complete metrizable spaces? We okay so far? Okay, let's carry on. I will put some sort of screencasts on the module webpage when I've got the module webpage sorted, which will be as soon as possible. Okay, so here's what we already said. The open interval is complete metrizable because it's actually homeomorphic to the real line. And because of that, you can find a complete metric giving you the usual topology on the open interval. A little exercise, if you've never checked that the open interval 0, 1 is homeomorphic to the real line, is exercise to find a homeomorphism between them. It doesn't matter which way around I ask this. Find a homeomorphism from 0, 1 to the real line. It's actually slightly easier if you start with an open interval like -1, 1 or minus pi by 2 up to pi by 2. And given that they're easier, you might do those first and then see how to do it for open interval 0, 1. But you could do it directly from the open interval 0, 1. Right, now, this subspace metric, actually this is a slightly non-standard notion. People often just use the same letter for a metric on the big set and what happens when you restrict that metric to the small set. But because I think there are some subtleties involved, I like to use this d tilde notation for what I call the subspace metric, when you restrict the metric on the big set to the metric on the small set. So you've got your big metric space xd, and you've got a subset y, well, y is a subset of x really, and you want to make y into a metric space. Well, you restrict the metric in the obvious way, but I give the metric a different letter. A lot of authors would just use the same letter, but the reason I want to give it a different letter is because, of course, d tilde could be complete when d is incomplete, and d tilde could be incomplete when d is complete, depending on the situation, the setting you're in. So d tilde and d, since they can have different properties, they must therefore be different metrics. And so I use this d tilde notation, but it's non-standard. And I think you'll probably find in many books either it doesn't get given a letter or it gets given the same letter. So it looks silly. You say d tilde from y1 to y2 is the same as the original distance, but because you're only applying it to fewer elements, that makes it a slightly different metric, which might have slightly different properties. Though obviously it's going to inherit lots of properties that the metric on the big space had. In particular, it has to be a metric. Now the fact that the subspace metric gives you the usual subspace topology, and if you don't remember about the subspace topology in topological spaces, that's again something to revise, is not instant. It's not completely trivial. It goes via results about unions of open balls and things like that. So it's not completely obvious. If you don't remember why the subspace metric actually does induce a subspace topology, it's worth reminding yourself. But we'll assume that as standard in this module. And it is nice that at least if you're working in a complete metric space and you want to know which subsets end up being complete when you give them the subspace metric, well, that's just the closed sets. There are various implications one way or the other way, and you have to be a bit careful. But if you're working in a complete metric space in the first place, then it's a if and only if. But what's much harder is to figure out which sets are complete metrizable. And this is on my challenging problems sheet. You can find proofs of it in the literature. You have to search for it a bit. One way is much easier than the other. So what's going on here? Well, you don't have to be closed in order to be complete metrizable, because, as we know, the open interval 0, 1 with the subspace metric from the real line is complete metrizable, but it isn't closed as a subset of the real line. Of course, it's closed in itself. Watch out for that. There are a lot of false arguments involved saying that things are closed or open in themselves. One example is on one of the question sheets, I think, where you have to prove that if you are homeomorphic to an open subset of the real line, every subset of the real line that's homeomorphic to an open subset of the real line must be open. And the standard false argument for that says, well, it's a continuous pre-image of an open set, so it must be open. But unfortunately, that proves that it's open in itself, which everything is. So watch out for that false argument. Okay, so what are the complete metrizable subsets of a complete metric space? Well, first exercise is a one-way implication. If you're an open subset of a complete metric space, you're complete metrizable. This will be, you'll be guided through this on one of the question sheets to see how this works. So there's a question on the question sheet which shows you how to do this. It takes advantage of the properties of the distance to a set function, which is again something that was dealt with in metric and topological spaces. So you take it, you start throwing in things like the distance to the boundary to help you have more information. And it being a nice continuous function, it doesn't do any harm to the topology that you're dealing with. But here's the general answer. And as I say, this is on the challenging problems sheet. If you've got a complete metric space and you want to know which subsets of it are complete metrizable, then it's exactly those sets which are G delta sets. What's a G delta set? It's something which is it's a countable intersection of some sequence of open subsets of X. Now, it's not at all obvious that this is going to distinguish the complete metrizable subsets, but once you know that the open subsets are okay, then there's a standard construction for figuring out what sort of metric you could try on the intersection of a sequence of open subsets by using, sort of making use of the metric on each set. There's a standard construction you can do. And that makes it relatively easy to show that if your countable intersection of open sets in a complete metric space, then you will be complete metrizable. The other way around is much harder and a very challenging exercise, and if you can do that, you should be very pleased with yourself. So that's on the challenging problem sheet. By the way, it's going to follow from some stuff we do later that Q is not a G delta set in R. Mainly because we're going to see, for various reasons, that Q can't be complete metrizable. And once you know that Q can't be complete metrizable, you can prove that it can't be G delta set. You can also do it directly using Baire category theorem. So exercise, but see below for various tools. So you can do it the Baire category theorem, or you can do it using one of the results we're going to get from the Baire category theorem. The rational numbers are a countable topological space with no isolated points. And no isolated points in the rational numbers, but they're countable. That stops you being complete metrizable. By contrast, I'll take away Q, the irrationals, that's this is complete metrizable. It's another one of these big differences between the rationals and the irrationals. In fact, it's a G delta set, which you can check easily. But actually, it turns out to be homeomorphic to the natural numbers via the continued fraction map. That's rather tricky details to check. So that's, of course, just an interesting aside. Turns out to be. It's homeomorphic to n to the n. That's a product of counting many copies of the natural numbers with the discrete topology. Sorry, you give the natural numbers a discrete topology, then you take the product topology on the countable product. We'll be doing infinite products in a bit. So if you're not familiar with taking a product of infinitely many topological spaces, it's not discrete anymore. Indeed, it's homeomorphic to the irrational numbers, which have got no isolated points. So it's very much not discrete anymore by the time you've finished. So that brings us to the Baire category theorem. This is an unbelievably useful theorem. For a start, you can use the Baire category theorem to solve. Please don't tell our current second years this. You can solve most of my second year prize problems using the Baire category theorem. Sometimes you have to be clever, but because they don't know the Baire category theorem, that makes it much more interesting because they have to find their own ways to solve these prize problems, which are of course much more interesting than using the Baire category theorem. However, some of those problems I don't know any way to do without the Baire category theorem, but others can be done from first principles. So if you go back and look at the second year prize problems, which I will include on in this module, but I will call them challenging problems 1 for this module. They won't be prize problems for you. And I've given you a hint that some of them can be done using the Baire category theorem. Yes, you could indeed find some second years, solve these problems using the Baire category theorem, and share the prize money with them. But that would be extremely mean of you. Of course, if any second years are listening to this screencast, then I've just given you a very big hint. So what does the Baire category theorem say? Well, it's got various different formulations. In sort of a pretty general form, it says that if you've got a complete metric space, and in fact, you might as well say complete metrizable, because it's a topological result. If you've got an intersection of a sequence of dense open subsets, then it's still dense. Doesn't have to be open anymore, because it's going to end up being, it'll end up being some G delta set. You can, however, if you want it to stay the same kind of set, the same result is true for dense G delta sets. So it's also true that if you've got a sequence of dense G delta sets in a complete metric space, then their intersection is a dense G delta set. So then at least you stay in the same collection of sets. I should have mentioned before, you may have been wondering, since I said that closed subsets of complete metric spaces are already complete, then that means, of course, they're going to be complete metrizable. So you can just check for yourself that every closed subset of a metric space is in fact a G delta set. So that's true anyway, and it had to be if what I've been saying before was true. Okay, so we're going to need a lemma in order to prove the Baire category theorem. And before we prove the lemma, we're going to need some notation. Watch out for the fact that the closure of an open ball might not necessarily be the corresponding closed ball. You get messed up by various pathological metrics like the discrete metric, so you have to watch out for that one. But in spite of that, we still use suggestive notation for the two kinds of balls. So here they are. So the open ball in your metric space X with radius R, I'll denote it this way. I've got the subscript X to remind you which metric space you're in. Now really, it should be X comma D, but that's a really unwieldy subset, really unwieldy subscript. The problem is, of course, you might well use more than one metric on the same set X, and then this becomes slightly dubious notation. But if you think of X as being the metric space, including its metric really, then this does make sense. But if you really wanted an absolutely safe notation, you could use the ball in XD centered on X radius R. I won't use that because it's too horrible, but that would be even more accurate. And even then you're in a bit of trouble, because you can have a formal definition of radius, and it's not necessarily the case that the radius of a ball of radius R is R, I'm sorry to say. Yes, you see, the definition of radius would be something like you look for all possible centres and you try and find the best one to make R as small as possible. And it might well be that the centre you've artificially chosen isn't the best centre for this set. Suppose you took the open unit interval as your metric space. Now, if you took the central point, a half, then this becomes the ball radius a half, centred on a half. If you take some other point, or indeed it's also equal to the ball centred on a half, radius 1, because every point is with strictly less than 1 away. But in fact, if you want a formal definition of radius, you know, the sort of the best you can do and take an infimum of things, you would say that's a set with radius a half or diameter 1 or something like that. Irritating technical things. These things don't happen if you're working in normed spaces or vector spaces and things like that. But there's all sorts of pathological, irritating things that happen if you're working in spaces that aren't things like normed spaces. Since we're going to spend most of our time with normed spaces in this module, the weird things don't happen. And radius really means radius, and diameter really means diameter, and so on, and there's no issue. Right, let's not worry about that. This is just terminology. If I say the open ball centred on X, radius R, this is what I mean. And since I won't give you a definition of the radius of a set or the diameter of a set in this module, at least I'm not planning to, this won't cause any problems. Closed ball, you put a bar over the top, and you get the corresponding closed ball. where distance is allowed to be less than or equal to r. So you get perhaps a whole load of new points which are distance exactly r away. Now, as I say, unfortunately, that's not necessarily the closure of the open ball. It is in norm spaces, but it isn't if you work in something pathological like the discrete metric space. And say you start looking at balls of radius 1. The open ball of radius 1 in the discrete metric, you'll get just 1 point. The closed ball of radius 1 with the discrete metric, you'll get everything, which is definitely not the closure of 1 point unless you've got only 1 point in the first place. So, again, in norm spaces, this won't be a problem. It will be that the closed ball is the closure of the open ball. And if we know where we're working, we don't need the subscript x. We can just say the ball, the open ball or the closed ball, centered on x radius r, a sensible notation. Okay, so now I want to come to a lemma which is like the nested intervals theorem. Now, nested intervals principle, or the nested intervals theorem or nested intervals principle, when you're working in R, or there's a d-dimensional version in finite dimensional space as well, and there's another version involving compact sets. It's basically about if you've got, say you work in the real line, if you've got a sequence of closed intervals, and each one contains the next one, then there has to be something in the intersection of all of them. These are when I say closed intervals, I mean, of course, closed and bounded intervals. So let me recall the nested interval principle. Let me put that up here. So if AN, BN are sequences of real numbers with AN smaller or equal to BN for all n, and so that the closed intervals are nested this way. A1, B1 contains A2, B2, contains, and so on. So these are nested decreasing. You could just say decreasing. Nested means that any pair, one of them is contained in the other. Nested decreasing distinguishes this from, for example, nested increasing or nested but indexed by the rational numbers or something like that. This is a nested decreasing sequence of closed intervals in the real line. Then, when you intersect them all, which is the same as saying the intersection over all natural numbers of A and Bn, bearing in mind that my natural numbers start with 1 and not 0, which varies from author to author, so watch out for that. But I should put that in brackets, is non-empty. So there's at least 1 point in there. If the length of the intervals tends to 0, then there's exactly 1 point in there. So if Bn minus An, which is of course the length of the nth interval, tends to 0 and then tends to infinity, then there's only room for 1 point in the intersection. Okay, so this, in fact, was done in first year I believe, in Nottingham. In second years was a more general fact about sequentially compact sets whose intersections come down, and then there has to be something in there, and if the diameters tend to 0, then there's exactly 1 point. So the sequentially compact set version. But now we're going to do a closed balls in complete metric spaces version, and it's subtly different, and I'll point out what you have to watch out for. Oh, sorry, does anybody need more time on that last slide? I went away. Anybody still need time to write that one down? Yeah, so I just bring it back. Okay, so when it comes to complete metric spaces, a subtle thing happens. It turns out that the conclusion becomes false unless you assume that the radii of the balls tend to 0. So it's no longer true in complete metric spaces that an intersection of a sequence of nested closed balls must have non-empty intersection, though that's a rather tricky and challenging exercise. What's slightly easier to check is examples of nested decreasing sequences of closed sets whose intersection are non-empty, because you can actually do that in R. So you can find a sequence of closed sets in the real line, nested decreasing, whose intersection is empty. That's a slightly easier exercise. But to do it with a sequence of closed balls, you have to invent a rather peculiar metric space to do it with, and that's much more fun. So that's on the challenging problem sheet. Okay, so let's have a look at this. Are we okay to move on? Good. Okay, so here's the lemma then. So now you've got a complete metric space, you've got a sequence at X, and you've got a sequence of radii you're going to use, some positive real numbers, which we insist converge to 0. And without that, the result becomes completely false. The intersection can even be empty, though it's hard to give the example. Then we suppose that the closed balls form a nested decreasing sequence. So in other words, we do exactly what we did before with the nested intervals. The first closed ball contains the second closed ball, and so on. Then the claim is there's exactly 1 point in the intersection. Now, this is actually quite an easy lemma to prove, but I probably shouldn't try and rush it, or I'll probably get it wrong. So I will postpone that proof to the beginning of next time. What I will do now is I'm going to discuss the statement of the Baire category theorem and some of the implications, and we'll come back and fill in some of the proofs in a moment. So let me remind you then what the Baire category theorem is about. So you've got a complete metric space. Again, it might as well be a complete metrizable space, and you've got a sequence of dense open subsets. Then we claim that the intersection of them all is dense in X, but it doesn't necessarily have to be open anymore, of course, because, as I said, the irrational numbers in the real line is a dense G delta set, and it's an intersection of this sort. But the irrational numbers are very far from an open subset of the real line. So that's the sort of setting you could be in. What if you miss out the word open, and suppose you've just got some dense subsets of a metric space? What could happen? Suppose you've got two dense subsets. Suppose you've got two dense subsets of a metric space. Does their intersection have to be dense? If you miss out the assumption open, what do you think happens? So just take two dense sets in a metric space, yeah? Which are both dense in the real line, intersect them, and you get the empty set. So if you lose that word open, you've had it. Obviously, if you lose the word dense, you've had it, because you could just take two sets that don't meet. So you're going to need both dense and open to have any chance. As I said, you can weaken open to G delta, and that's probably about as far as you can go. There are other versions of this, but as I said, you've got to watch out for those sorts of examples. Easy examples which show that if you don't have all the conditions, something horrible could happen. Now, in any metric space, it's easy to show that an intersection of finitely many dense open sets is still dense. And if you're intersecting finitely many open sets, it'll still be open. So the finite intersection thing is not interesting. So if you intersect 1, it's dense and open. If you intersect 2, it's dense and open. If you intersect 3, it's dense and open. And so by induction, if you intersect them all, it's still dense and open, right? Well, we've already pointed out that it doesn't have to be open anymore. And if you're not in a complete metric space, if you're in an incomplete metric space, it doesn't have to be dense anymore. It can even be empty. In fact, that happens with rational numbers, because if you throw away 1 point from the rational numbers, then you get a dense open set. If that gives you 1 for every rational number. Let's have a look at that example. Set x equals q, and let's have a new page for this. For q in q, set u sub q to be q take away that point. Oops, that should be just q take away 1 point. Then it's easy to check that uq is a dense open subset of the rational numbers. But if you intersect them all, that's a countable intersection, because there's only countably many rational numbers, you get the empty set. Now that is open in Q, but it's not dense. So what? We knew that Q wasn't a complete metric space, but this, if you think about it, solves one of the exercises I mentioned earlier. And then you could do the same thing, but work with the. You could do modifications of that to get an example where you're not open. The empty set is open, so you wouldn't use this example. So proof by induction is clearly rubbish, because that would have worked in any metric space, and this example shows it's not true. So, so you have to think about the fact that things go wrong in the limit. When it's an infinite intersection, it might well be very different from the finite intersections, as it is in this case. Intersect finitely many of these, and you've still got a dense open set. Intersect them all, and you've got the empty set. So that's a big change at the limit. So it's a topological result. Denseness doesn't use the exact distance. Denseness can be stated purely in terms of meeting open sets. If you don't remember exactly the theory of dense sets in topological spaces, again, that's something to discuss on Friday. And there are lots of equivalent definitions of dense, but the standard one that I like to use is a purely topological definition of dense, and that doesn't care which metric you use as long as you've got the same topology. And open, of course, doesn't care which metric you use as long as you've got the same topology. So all this stuff about dense open sets and non-emptiness doesn't care which metric you use as long as you've got the same topology. So if you're complete metrizable, that means you can get this topology by using complete metric, and then the result applies. And so Baire category theorem is really a result about complete metrizable spaces. And then, as I mentioned before, if you work with G delta sets instead, you meet the fact that if you intersect countably many countable intersections of open sets, it's still a countable intersection of open sets. So you get this corollary, that if you've got a sequence of dense G delta sets in X and you intersect them, it's still a dense G delta set, which is a slightly more natural formulation from the point of view of the fact that at least the final set is of the same type as the earlier ones. But you don't normally use this version. You normally work with the dense open sets version, or some corollaries of it which are coming up next. But I think that's a good place to stop today.
Just one more question.
Oh, yes?
Theorem 1.5.
Yes?
It's called Baire category theorem.
Yes.
So, in which way is it actually involved in category theory?
Oh, it's not about category theorem, but Baire used some language of, he talked about sets of first category and sets of second category. And he expressed his theorem in terms of that. Now, I can never remember which way around is which. It's to do with, we'll be talking about nowhere dense sets in a bit. And so he expressed the theorem in terms of, that it's impossible for, he said, no complete metric space can be of first category in itself, or something like that, which means that it can't be a countable union of nowhere dense subsets. So it's a different use of the word category. It's an older use, nothing to do with category theory.
Okay.